Hello, this is Jack Jackson. In this video, we're going to be looking at one of our basic rules for derivatives. Remember, one of the ways that we can combine functions to get new functions is by adding them together. So let's start here with our blank canvas here, and we graph a function f of x. This one is 1/10 x squared. So we have a transformed power function there, or a quadratic parabola. And then we have a nice little sine wave going here, 3 sine of x. It's been stretched vertically by, so it has an amplitude of 3 from the basic sine wave. And we can consider some point A along here controlled by this slider, or by this controlled by this box here. So for example, right at the moment there, A is 6, and you can see where f of A is this point, is the y value of this point here. It's about 3.6, and g of A is this point here, which is negative 0.84. And then the way we get the sum, let's see how we do that. So I'm going to click on this sum illustration 2. So if you look at those vectors right there, there's some of the vectors that we could be looking at for the second function, the g function. And so for integer values, these directed line segments tell you the value of the second function. And we want to move those from the y equals 0, from the x-axis, to get to the points on the graph of g of x. But if we take those and take this slide for translation slider and slide it slowly up like this, we will see those points, those vectors being moved. And notice when they're being moved, they're staying the same length. So they're just being slid up or down, in this case slid up, so that what happens is they now start at the curve f of x, and from there we move the amount of g of x. And if you look, where they end up is going to be on this curve of s of x, which is f of x plus g of x. And you can see that in the numbers here for a particular a value. Here's the value for a, f of a, and g of a, and s of a. If you just add the f of a and the g of a together, you get the s of a. So you can kind of convince yourself that that works. There might be a slight bit of rounding off problem here with this, but basically these should add together correctly. We're adding a positive and a negative here, so how do we get that? So in this case, we go up to f and then back down by the amount of g to get where we are on s. The sum illustration 1 does the exact same thing, but it does it just for one particular point instead of a bunch of them at a time. But that point can be set wherever you want, not necessarily the preset ones on the sum illustration 2. So hopefully you can see what that does. This one is kind of interesting, because if you look at this, the parabola, of course, is the quadratic function gives us this parabola shape, okay, between a u and a v kind of a shape, and then the sine function gives us a wave. So we might use the sine function to denote something that goes in a cycle, like a seasonal cycle, for example. And let's say if we're just looking at the positive part of this, we might have something that would be modeled by this red function, which would indicate something that has a seasonal fluctuation. Let's say the sales of something that depends with the season, something you sell more of in the summer than the winter, for example. And so we see the peak in the summer and the valleys in the winter like this, but the overall thing is growing along this quadratic curve here as well. So this center line here has now become this quadratic function here. So that's a good example of what happens when you're talking about these kind of sum functions, sum of two functions. Okay, so let me turn off that sum illustration, but leave these functions here. Now, I have the values of the derivative here, there's f prime of a and g prime of a, and there's s prime of a. Those are the values of the derivative at this particular x value. That is the slope of the tangent lines at those 3 points on those curves, all with x equals a. So here's my question. Do you see a relationship among those 3 numbers? Look at those numbers and see if you can figure out a relationship among those numbers. Did you figure it out? Let's take a look at if we change a little bit. Let's just kind of arbitrarily go over here. Do you still have the same relationship? Now remember, this time g prime of a is negative, and so is s prime of a. Does the relationship still work? What about at a different place? What about here? Does it work there? What if I put in something like maybe 7.5 here? What did you think? Well, did you see that maybe these 2 numbers here add up to this one here, just like it did over here? Well, we can illustrate that, and remember that the derivative comes from the limit of difference quotients. Okay, so let's first start looking at it at the difference quotient level. So at the difference quotient level, what we're looking at are slopes of secant lines. Okay, so we have our point of interest here on each of the 3 curves where x equals a, right now 7.5. And we find a nearby point, in this case h units, okay, which is 1 to the right. In this case, a plus h is this one here. So this distance between these 2 is h. And then we find a nearby point there. So this is, for example, this is a f of a, and this is a plus h f of a plus h, and so forth for the others. Draw our secant lines in and find the slopes. Now remember, the slope of a line is how much that line goes up or down when you go to the right one. Since it's a line, it has a constant slope, so it doesn't matter where we start. So if we start at our point of interest and go to the right one, let's say here, and see how far the function goes up or down, that amount is our difference quotient. So the difference quotient for f is the length of this green vector, and that is the slope of this green line right there, that green secant line. Similarly, the slope of this blue secant line down here is that little bitty vector right there, how much it goes down when we go to the right one. And similarly for the sum function, when we go to the right one here, we go up by this amount. That's the slope of that line. So once again, I can take this, if I reset it to 0 and I slide it up, watch what's happening. I'm going to slide it up so that we start okay, look, the green vector is going to move up to here so that it starts at the bottom here at s of a, right here. And it's going to go up by the green amount, and then from the end of that, we're going to come down here. Of course, that's going to be adding those 2 amounts together. Okay, adding a positive and negative means you go forward some and then back down, up some and then back down some. And so we end up there, and sure enough, the difference of those 2 is exactly the same as what we had here. You can see it numerically over here, and we can see it visually there. If we pick a different point, let's say here. Here we have amount here that's going up. Another one here. Everything's going up here. If we slide this, going up by the green amount, and then the blue amount is the same as going up by the original red amount, which is all the way from here up. Okay, and you can see that play out. Now, if we start secant lines, we can pick any number we want for h. This one will allow you to go from like -3 to 3. But the point is we want to take now the limit of this process as the h approaches 0. If I were to actually type in h is 0, this thing will be undefined. All that stuff disappears when h is 0. But if I put in something close to 0, like say 0.1, we're getting closer and closer, or pretty close to the tangent lines. To see that, I can take away the difference quotient 1 and say, look at the derivatives. Now what we're doing, the h doesn't affect anything here, but what we're doing here is we're looking at the tangent lines now. So this time, these 3 lines that we see are tangent to the function at these different points, all with x equals a. And in each case, we go to the right one, and we see the slope being this vertical change on the tangent line when the horizontal change is just going 1. So this vector here, that length represents g prime of a, which is 2.93. So that's 2.93 in length. Let's just zoom in a little here. And this green one represents the f prime of a, which is 1.3. That's this distance here. And if you add those two together, you're going to get s prime of a, which goes from here up. And again, you can see that by just taking those vectors, moving them up, and putting the end to end. You see that they do add up. They're not changing length, they're just sliding up there. And of course, visually, that gives us a geometric or visual picture for it. And over here, it gives us a numerical thing. And so we see that those two derivatives do add together to give you the derivative of the sum. Okay? Now, this is true at the point level. We can do this for any by changing points, changing the point A. This relationship is still true, no matter where I am, whether I'm over here or if I'm somewhere in here. It doesn't matter if they're both negative, one's positive, one negative. It still works out no matter what. But the point is, this is doing for a particular number at a particular point. But since this is true no matter what we pick for A, we should be able to say this is true for functions. Now, to illustrate that, I'm going to turn everything off here, reset the slider back all the way to the left. So we start with a kind of a clean slate here, and let's look at the derivative functions. So we could probably guess the derivative of this quadratic. Let's just go back there, kind of get an idea what the derivatives might look like. So this is concave up everywhere, so the derivative is going to be increasing. The derivative, this is negative slopes here and positive slopes here with the 0 slope here. So the derivative should go through the origin, should be positive, should be first quadrant over here and third quadrant over here. And it turns out when you take the derivative of a quadratic, you get a straight line. So we're going to get a straight line through here. And if we take a derivative here of a sine wave, you also get another wave, right? So the derivative here is a slope at this point right here. And that's as big as it gets. It's also the inflection point. Then this is concave down, so the derivative is going to start up here, actually at 3, and it's going to come down. It hits 0 right there. Negative slopes here, so it's down below, and so forth. We get another wave. So anyway, here are what the derivative functions look like. So the derivative of that quadratic, the derivative of f, was this line here. The derivative of the sine wave is this wave here. It's actually a cosine wave. And then here we get the derivative of the sum function, which is the sum of the derivatives. So the conclusion is that the derivative of f of x plus g of x is f prime plus g prime. And once again, I can sort of see that by picking an arbitrary a value, and I can slide that up and see that that does get me to the function of s prime by just adding together the f prime and g prime. So ultimately, there's our conclusion that let's leave it like this. The derivative of the sum is the sum of the derivatives. We've seen that. Hopefully this gives you a nice visual for why it works. It works at the difference quotient level, and so when we apply limits, that works at the derivative level as well. And we can see visually what's going on. But of course, formally, we need to prove this. And so here's the proof. Okay. The derivative of the function f of s, which is the function f of x plus g of x, is the limit as h goes to 0 of s of x plus h, which is f of x plus h plus g of x plus h, minus s of x, which is f of x plus g of x, over h, and then take the limit as h goes to 0. That's the definition of the derivative. Now what I'm going to do is I'm going to distribute this negative here, get rid of the parentheses here, so I'll get f of x plus h plus g of x plus h minus f of x minus g of x, that's all g of x, all over h, and then take the limit as h goes to 0. Now I'm going to use the associative, that was the distributive property. Now I'm going to use the associative commutative properties to rewrite this in a different order. I'm going to rewrite it so the f's are together and the g's are together. So I'm going to swap the order of these two middle terms here. And then I'm going to group the first two and group the last two and write them both over h. So that's basically the definition of addition of fractions. That's how that works. Or the distributive property, if you want to think of distributing 1 over h. And now the limit of the sum is the sum of the limits, provided those limits exist. And if this limit exists, you can see that's exactly the definition of f prime, and that's exactly the definition of g prime. So the derivative of f plus g is f prime plus g prime. And so there's the actual proof of it as well. So hopefully this gave you a formal proof so we can see what's happening with the algebra and the formulas there. It also gives us a visual for it as well. And we were hopefully maybe even able to discover that as we were going along. Now, ultimately, what this is going to do is going to give us a nice little rule that we can use to find the derivative of a sum, because if we can think of this as the outermost structure is a sum of two things, then we can break it down into two derivative problems where we take the derivative of each piece. Hopefully we already know how to do the derivative of each of those pieces, or at the very least it makes each one of those a little bit simpler derivative to work out. And so this gives us a nice little shortcut rule. And since we proved it once and for all here, we wouldn't have to go back to the derivative definition like we did here in the proof to continue on with that. All right, hope you enjoyed that. See you for the next video later. Bye-bye.